Okay, so now you know that the more active metal will undergo oxidation and the less active metal will undergo reduction. And the further apart they are on reference table J, the greater the chance that the reaction will take place. Now, we can actually calculate something called voltage based on this by getting what's called the oxidation potential of the more active metal and the reduction potential of the less active metal. And adding the two together will give us what's called the voltage or electromotive force of this reaction. It's kind of like this. You have water at the top of the hill, you have water at the bottom of the hill. You can calculate the potential difference between those two levels of water. The potential difference between the oxidation half reaction and the reduction half reaction, that's what's known as voltage. Total voltage is equal to the voltage of the reduction half reaction plus the voltage of the oxidation half reaction. If the voltage is negative, that means the reaction is not spontaneous, which means you either made your battery backwards or you just can't use the reaction to make a battery. If the voltage is positive, that means the reaction is spontaneous and you can use it to make electrical current. Okay, first, in order to get the voltage, let's find the charges of all the species in this reaction. Lead has a charge of 0, aluminum has a charge of +3, nitrate is -1, lead is +2, nitrate is -1, and aluminum is 0. The oxidation half reaction would be, well, lead goes from 0 to +2, so Pb0 becomes Pb +2 by losing 2 electrons. And the reduction half reaction, Al starts off as +3, ends up as Al0, which means 3 electrons are gained. Now, where are we going to find out the voltages of these two half reactions? The AE reference tables. This is a reduction potentials table. It gives you a list of reduction reactions and the reduction potential in volts. These are just reduction reactions. Notice that in every case, the charge becomes more negative and the electrons are on the left side, shown absorbed, gaining electrons. So why don't I have a separate chart for oxidation? Because I don't need one. All I need to do if I want oxidation is just reverse what's written here. If I reverse the half reaction, I need to reverse the sign of the voltage as well. So let's take a look at the two half reactions that we had. We had lead being oxidized. Well, here is the half reaction for the reduction of lead 2 to 0. So if we were to write this as Pb goes to Pb +2 plus 2 electrons, instead of the voltage being -0.13, that's the reduction potential, the oxidation potential would be +0.13. The other half reaction was the reduction of aluminum +3 to aluminum 0. Now that's the reduction half reaction right there. Aluminum +3 gains 3 electrons to form Al0. It has a reduction potential of -1.66 volts. Do I reverse it? No. I only reverse the oxidation. The reduction, this is a reduction potential, so I use that potential. So lead has an oxidation potential of +0.13 and aluminum has a reduction potential of -1.66. Okay, so lead had a voltage of +0.13 volts. And aluminum had a reduction potential of -1.66 volts. To find the total voltage of the cell, we just add those two numbers together. +0.13, -1.66, that comes out to -1.53 volts. Since the voltage is negative, we cannot use this to make a battery. But you know what? If I reverse this, if I made it aluminum plus lead nitrate instead, that would reverse the signs and make the voltage +1.53. So the reverse of this reaction could be used to make a battery. Calcium has a charge of 0, hydrogen is +1, chloride is -1, calcium is +2, chloride's -1, and the hydrogen is 0. And I've included the voltages here so we don't have to go back to the other reference table. The oxidation half reaction is calcium 0 becomes calcium +2 by losing 2 electrons. The reduction half reaction is H+1 becomes H0 by gaining an electron. But notice that hydrogen is diatomic over here, so I need to take that into consideration and double these other things as well. That would be the reduction half reaction. Now let's get the voltages from the reference table. The reduction potential for hydrogen is 0.00 volts. Now that doesn't mean that hydrogen doesn't reduce. The way they got these voltages is they made batteries of different metals with a hydrogen electrode. And all the voltages that are on the table are compared to what's called the hydrogen standard. So the hydrogen half reaction has a voltage of 0.00 volts. That's because that's just what hydrogen was set at as the standard. Calcium has a reduction potential of negative 2.87. But this is oxidation, so we're going the other way. So we're going to reverse the sign to positive 2.87. When you add these two voltages together, you get positive 2.87 volts. So yeah, you could use this to produce electric current. It would give you almost 3 volts of electricity. So is this spontaneous? Yes. The one prior to that with a negative voltage? No. So let's find the voltage of the first ever manufactured battery, the zinc-copper battery. Zinc starts off with a charge of 0. Copper plus 2, sulfate minus 2. Zinc ends up as plus 2, sulfate still minus 2, and copper is 0. So the oxidation half reaction is zinc 0 becomes zinc plus 2 by losing 2 electrons. And the copper plus 2 picks up 2 electrons and forms copper 0. Let's get the voltages from the reference table. So first, for the oxidation of zinc, well, this is the reduction of zinc, so we'll make it go opposite, and we'll change the voltage from negative 0.76 to positive 0.76. And copper is reduced. Now you got to watch out for copper because there's actually 2 copper half reactions on this table. One is for copper 1 becoming copper 0. The other is for copper 2 becoming copper 0. In our reaction, we had copper 2 becoming 0. So that's the half reaction we're going to base it on. And we're going to keep the voltage the same, positive 0.34 volts. And when you add those two together, you get positive 1.10 volts. So this reaction can be used to generate an electrical current. It'll give you a little bit more than 1 volt worth of current. Now what this all means is that fluorine has the greatest potential to be reduced. Doesn't that make sense? Fluorine has the strongest electronegativity. It has the greatest ability to attract electrons of any element on the periodic table. So it would make sense that its voltage, its reduction potential, its ability to gain electrons would beat out everybody else's. And just like on reference table J, where lithium is the very top most active metal, lithium, even though it looks like it's listed on the bottom, it might have the biggest negative reduction potential. But what does that mean for oxidation potential? It has the biggest positive oxidation potential. Lithium is the element most likely to undergo oxidation. So think of this reduction potentials table as kind of being an upside down version of reference table J. Lithium is the most active metal. Lithium is the most likely to be oxidized. Gold is the least active metal. Gold would have the greatest potential to be reduced. So lithium, lithium, rubidium, rubidium, potassium, potassium, cesium, cesium, barium, barium, strontium, strontium, calcium, calcium, sodium, sodium, and so on. So this table matches reference table J, but because the top ones on table J are oxidized, and the top ones on this reference table are most likely to be reduced, just think of this as sort of an upside down version of reference table J with the actual voltages for the half reactions given to you.